This is Chrisferb, and I'm going to review a chi-square goodness of fit test. And this type of test is a little bit more difficult than the prior dice problem one that I did. This one, we are trying to see if our data follows a binomial distribution, which makes it a little bit more tricky. Okay, we'll get started. Okay, sample of data is thought to follow a binomial probability distribution. Perform a chi-square goodness of fit test to determine if the data appears to follow a binomial distribution with p equaling 0.5, n of 4 to a 5% level of significance, or 0.05. So these are all inputs for our binomial, which we reviewed in some of my other videos. Okay, so that's our probability of 0.5, and then 4 to a 5%. Okay, here's all the data right here. So we have, these are the values. We're looking through 0 to 4, and then observed, this is actually what we ended up getting. Take, for instance, we grabbed a handful of this data out of something else that's supposed to follow that distribution. Okay, so I have this listed out here to save us some time, so that's good. So the trickiest part of this whole thing, there's a couple parts, of course, with the chi-square goodness of fit test, but the big deal is we have to figure out the probability, the proper probability of what should be for each of these values. Now, because we're looking for the binomial and we're trying to test it against the binomial, we have to figure out the proper probability so that we can figure out what the expected should be. So the probability is a big part of this. And this is why dice problems are super easy, because we know what the probability should be. With binomial, we have to do some calculations. So we are going to go to our calculator in this case for our binomial part here. And I'm going to pull the calculator over. And we're going to do this on a TI-83 84 variant. Okay, so the first one is, you see 0. So I'm going to turn it on, hit clear, and I'm going to go into second vars, which gives us the distribution. Let's see. Okay, so it's second vars, which is actually second than distribution. So if I go up, it brings me to the bottom. Sometimes that gets us quicker, maybe not. And then I'm going to go and I'm looking for the binom PDF. And that's because we're looking for specific findings for this probability. We're not looking for cumulative data. So I'm going to go to binom PDF, hit enter, and now the number of trials. So the number of trials in this case is 4, because this is our 4 right here. Okay, so we do 4, and then our p is 0.05, or 0.5, and it's this p right here, 0.5, and then the value is actually the 0 right here, because that's the category that we're looking for. And hit enter, and we get 0.06. It's going to be hard to write in here, but we end up getting 0.0625. Okay, and then to save time of going back and going through the whole beginning of the menu, I'm just going to go up and pull it down. So I hit the up arrows right here and hit enter. So I pulled down my little function, and then I'm just going to go back and change this to a 1, which is right here. All the other data stays the same. So I'm just going to change that to a 1. Go back on the outside of the parentheses and hit enter. And that gives us our binomial probability for the 1. So that is 0.25. And then I'm going to do that for the rest of these. Pull it down, go back, 2, and then hit enter. And I get 0.375. And I'm going to write in just the last 2. Okay, the last one is 0.25, and then 0.0625. A little bit hard to fit in there. Okay, so now all we do is we take this probability of each one of these and we multiply it by the total of the observed, which is the total that we have of the observed selected, regardless of which value it is. And the total for this is it's 283. So it's 283 if you add this all up. So when we multiply 283 times this value right here, I'll move the calculator. It's in the way. When we multiply 283 times this value, or the probability, gives us the expected, because theoretically out of 283, something that has a probability of 0.06 should come up a certain amount of time. And so we multiply that. I'll write in the numbers here. We get 17.687, and then for the next one we get 70.75, and then we get 106.125, and then we get 70.75, and then the last one 7.687. You see the pattern there, the way it works. And then we're going to find the difference from observed and expected, and I'll write these in. So that's observed, expected. So just observed, subtract expected. And we have 3.313, and then negative 12.75, 3.875, and then 7.25, and then negative 1.687. Okay. And then when we go and we take this and we square it, and I'll write these in, it is 10.975, 162 point, and then it's 562. Almost made a mistake there. 015, and then 52.562, and then 2.845. And then we go and we take the squared and we divide by the expected, and we get this 0.620, 2.297, 141, that's 0.141, and then 0.742, and then 0.160. And then when we add all these up, this gives us our calculated statistic, and we end up with 3.96. So that's our calculated statistic, which we're going to use to compare to our critical value. This is my artwork here. Okay, now we need to find the critical value, and the critical value is based on degrees of freedom. The degrees of freedom are always the number of categories, 1, 2, 3, 4, 5, minus 1. So that would be 5 minus 1 equals 4. And then it's based on our significance level, which is 0.05. So our critical value is going to be so it's degrees of freedom 4, 0.05. I'll grab the chi-square. So that's degrees of freedom 4 and 0.05. So 4, 0.05, 4, 0.05 is 9.488. Now I need to remember to back out here, otherwise everything is going to be big. Okay, so that was 9.488. Okay, so that's our critical. Okay, so we're going to put this on our drawing. So we go 9.488. I'm going to draw some rejection zone lines. And now we're going to place our calculated value. Not even close. So it would be like right there. It would actually be back further. And just because of the difference, one's 3 times smaller. So what that means is, it appears we are, we're going to write down, do not reject HO. It appears to follow the binomial, which is what it means. So, do not reject HO. It appears to follow the binomial probability distribution. And when I made this, you can kind of see that I made it so that it roughly matches that, because it starts small and then towards the center, it's one of the largest numbers, but these numbers are pretty big, and then goes small again. So it has a similar type of curve to something that would have a 0.5 on the probability for that type of thing. So it doesn't follow it. Thank you for watching.